So I now pass the baton to Dr. Michael Bussmann. Thank you very much, Professor Gao, and I hope to see you later on, either in the breakout sessions or during the whole conference. Thank you very much. So
I apologize for being late. I'm at home today, and yeah, let's say I need a better internet connection.
No problem, no problem. I think we had a lot.
Thank you very much for your patience.
That's fine. We had a lot of questions for Professor Gao, so we managed to stay engaged. So I just going to briefly introduce you. Dr. Bussmann is a theoretical plasma physicist working on the interface between large-scale data analytics, exascale simulations, and scalable AI. He has founded the Center for Advanced Systems Understanding as a new science institute to study complex systems using novel digital infrastructures for studying both forward and inverse problems. Examples of his work include the generation of accurate models using AI for the interiors of exoplanets, AI support for decision-making in clinics, and AI for fast data analytics at large-scale research facilities. His current focus is on scalable AI models with provable accuracy in predicting the evolution of complex systems. So please join me in welcoming Dr. Bussmann, who will talk about digital twins of matter under extreme conditions, where exascale meets AI.
Thank you very much for the invitation. And again, I'm sorry for the delay, and we'll jump right in. So what you see here is a wonderful picture of Jupiter that has been taken by NASA. And we now get a lot of data on not just our planets in our solar system, but also from exoplanets. However, we have the problem that we basically always just scratch the surface. So we have to understand really what's going on inside the planets and also in other complex systems of matter under extreme conditions. And I'm going to show you a bit on how we're doing that. And one of the possibilities we have is to actually recreate those states of matter that we cannot directly observe with our observatories in the laboratory. And one of those facilities is the HELMholtz International Beamline for Extreme Fields, which is hosted by HCDR and European Exascale. And this brings a high power laser. And with high power, I really mean petawatts of power almost, and X-ray free electron laser together at one place. And the X-ray free electron laser can actually be used to probe the matter at atomic scale, so really get almost atomic resolution of the processes that are happening here. And I here show you a small promo video of that to give you an idea on how complex the full machine is. This is, for example, just the particle accelerator that creates the electrons that then create the light used for the free electron laser that then can be used again in this chamber to probe what we are driving with a high power laser. So you see the whole facility by itself is a really complex machine, and we want to always have it work at optimum conditions. However, optimum conditions are not fixed. They are driven by the science we're doing at these facilities, and each individual experiment is actually very different. It's complex by itself in the sense that it needs different detectors. It is a fully different system, and at the same time it needs to give the information of what is the best use of the machine back to the machine in the end. So for now, we're not just setting, but we're setting conditions and hope that these are the best conditions. And with our personal expert judgment during an experiment, which is usually a 24-hour a day adventure, I really have to say, we have to say we have to make these experiments successful by really putting in our full judgment of what we're doing during these experiments. And since these are experiments, we never have all the information in the beginning of what to do and how to set up those machines perfectly. We have a lot of information ahead, but some things are new. And this really poses a challenge. And I'm going to show you why this poses a challenge and how to attack this challenge. But to give you a bit of idea on what we're talking data-wise here is that such a machine as the European free electron laser can actually give you 27,000 shots per second. So we can reach up to 27,000 images per second in theory. However, the detectors that we use, the imaging detectors, also have to work at these. And we have here, for example, a large megapixel detector. We know that our mobile phones have much more pixels, but this is a huge detector by itself because it can deliver really up to megahertz image rates at high resolution, high dynamic resolution. And this is just one of the detectors that is typically used in such an experiment. And as I said, each of these experiments is different. It's different if we look at the interior of planets, but it's also different if we look at the dynamics of hot plasmas, for example, that are interesting for fusion research. And one of those very nice things of this kind of installation that it can even look at application areas that you would not suspect. And one that I really want to choose here is cancer research. And this is developing new sources for irradiation of cancers using lasers and very simple targets. And here's a simulation, and I'll come back to that later on. The idea behind this is that typically for irradiating cancer, we are looking at X-rays. But X-rays usually can also harm the surrounding tissue, while at the same time, using that they are made of actually can focus the damaging radiation really to the tumor and not harm the surrounding tissue.
Michael,
these installations have been...
Sorry, I think we may have internet problems. I would suggest maybe to turn off your video.
Okay, I will switch off my video.
Yeah, sorry for that.
I told you I'm at home. Okay, I hope this is going better by now.
Okay, fantastic. Thank you.
Thank you very much. So what we want to do is really make these ultra compact and also use the special characteristics of these sources because they can deliver much more radiation in a very short burst. And this can potentially kill the cancer much better and reduce the number of reoccurring cancer cases in patients. So this is a very promising setup for investigating this. However, these are still in their infancies in use for clinics. So we really have to make these sources reliable. And that's how they look right now. It's basically a large laser shooting on a small foil. So this is what you should have in mind when you're thinking of a particle accelerator by now. It's an aluminum foil that a laser can shoot on. Sometimes these are more complex targets, but this is about it to remember. But the problem is once you're looking really into the dynamics of what the high power laser does to the experiment, you see very different dynamics depending on the target and laser parameters. And here are three cases, and what we're talking here about are instabilities of the plasma. And the plasma has the very big problem that it is a nonlinear system. So once I change the parameters a bit, it will strongly change. And the information we get are not these nice real images from the X-ray laser, but we get these scattering images. And this is a loss of information. And the inversion of this problem is in fact a non-convex problem. And if we now increase energy of the high power laser to go to clinically relevant energies, those instabilities really show up, but we now have to decide which one is it, A, B, or C, just from the scattering picture. And you see they are different, but they do not contain the whole information that we need. So what we are doing is basically developing a full digital twin of those experiments, where we are not just having the experiment itself, but also the input from the X-ray laser, the input from the high power laser, knowledge on the target, knowledge of the detectors and everything else. So we can directly integrate this into the whole research facility. And the problem with this is that the system we're looking at is actually a system that we need to look at theoretically using exascale simulations. So this is one of those simulations performed at the Summit supercomputer. And this just drew 8 megawatts of sustained power on this system just to look at this system and simulate this system. So this is huge. And giving that much input to a neural network is a challenge by itself. So just remember, we're now having 10 trillion particles, 400 billion cells, 28,000 GPUs. That's what we're talking about. This is petabyte size per hour data rates, really. And in order to go there, we now have the problem of streaming data from simulations, streaming high quality data from detectors, and bringing all this together at a time of about a week, where we need to make tough decisions on how to really perform the experiments at those facilities optimally, because those experiments typically cost on the order of 100K euro per week. So this is really expensive. And this is what we're planning to do, and this is where we're making big progress. So we're really trying to reduce those large-scale HPC simulations to surrogate models that are also informed by measurements that we're taking at different experiments, and finally create a surrogate model for the experiment we are planning that is also invertible. So the very first step is to go to streaming learning, to not just put these petabytes of information to disk, but really directly stream into the AI model. And this leads to exascale workflows where we couple different simulations that simulate different parts of the experiments, the detectors, the detected signal, the system itself, the light sources, everything is simulated. And this is streamed live through the memory of the system. And at the same time, on the same HPC systems, we let run our AI. So we're never going back to the file system. So we have to take care that the data quality is right, that we're taking all the data that we need. There are lots of problems here that we have not yet all tackled, but they are interesting to solve in the end for streaming AI. But once we have done that, we reach something like this. So this is still based from file output, but we get very nice results for these very complex problems, so that we can mimic, for example, the energy spectrum of particles generated by the highly nonlinear interaction of the high power laser with a target. And what we're doing is we're using invertible neural networks. So we're using not just physics-informed neural networks, but they're also invertible in the sense that we can switch from the observed quantity back to the theoretical description and vice versa. So this means that we can, at medium to very good accuracy, depending now on the processes we are currently looking at, reconstruct very well the parameters describing those particle sources. But of course, we finally want to go to a full description of the system. And for that, we really need to stream all that data that we have in that system into our AI model. And this is one of the first results to look at. This doesn't look like much, but this is really the full 6D phase space of all the particles in such a simulation. And this is fantastic because basically this, together with the electric and magnetic fields that are generated, is the whole information you need on this system. If you have this 60 phase space reconstructed, then you're very good at describing the system by itself, because this is all the information that is really needed. And you already see those on the scales down here, that these are log plots. So you see that actually the accuracy is not that bad at all. You also want to go do this to go for real-time interpolation of data during experiments. You really have to make this fast. And in order to do this, you do not just take the input from the simulations, but you also take the input from all the modalities you have, from all the sensors and detectors you have, and join them into a single surrogate model that can also again be inverted. And this is very important because, as I told you, one modality by itself, the inversion of this is a highly non-convex problem under nonlinear conditions. And so the more different modalities you have that have different views on that system, the higher the probability that you get only one parameter set finally describing that system. But for that, in order to really do that, we need scalability. And here's our solution to that, really using gating and dividing the problem into sub-problems so that we reach very high scalability. This is only running on 60 NVIDIA B100 GPUs, but we are currently setting this up to run on really HPC scaled systems of a few thousand GPUs and see how the scalability will look like. But I'm pretty confident that we will see similar strong scaling here. On the other hand, we're developing new algorithms. Here's one example of really interpolating this much better using fast or provenly fast schemes for high dimensional interpolation. And as a result, we have here a very nice example where we use the fashion MNIST data set, and we use this interpolation to get to increase the quality of the Jacobian, and really we get the full rank by regularization with the Chebyshev nodes we have selected with this interpolation scheme, and compared to standard autoencoder schemes, this gives much better results in finally reconstructing the high-dimensional underlying space. So finally, where we want to go is reduce the petabytes per second information to a few parameters. That would be fantastic because we can do this in experiment. It's directly an information on the physics of the system that we as experts can understand and assess in their quality. And it can also greatly reduce the problem of having to keep this data for longer time, because petabytes per second data is hard to keep in the end. And here are some first results on really reconstructing those scattering images and getting real space images from the scattering signals. So this is one of those examples for solving the non-convex problems of phase retrieval and comparing this to state-of-the-art technologies. And you already see that comparing the ground truth to the NN kernel, you of course see some transformations like motion in X and Y of the final sample, because there are several solutions that can lead to the same scattering image. But in the end, knowing those symmetries of the problem, we can reconstruct precisely the final ground truth as seen here. And with that, I want to finish. This is just the start. So when we have implemented this finally for experiments, and we have to redo this for every experiment, so this is very expensive, but some technologies might help in reducing this expense. The next part would be to give, of course, the feedback to the machines, to the laser, to the X-ray free electron laser, to the detectors and so on, to give more information on what are the optimum conditions for the experiment. Because now we would be able to understand the experiment and give feedback to the machines so that these very complex machines can be moved to the optimum experimental conditions. However, this, as you know, is a complex problem by itself. Such a particle accelerator can have millions of free parameters that you can set. So in the end, again, we will be faced with the challenge of having probably to use AI to set those complex machines to the optimum working conditions. But the possibilities here to really give feedback to the machines and make more accurate and better experiments in the future. And with this, I'm finished, and thank you very much for your interest. And I almost stayed in time now because I sped a bit up. Thank you very much.
Thank you very much, Michael. Very fascinating talk. I think you're really proving the value of leveraging AI models from a different perspective than the previous speakers have discussed. So this is actually very interesting, and I think we may have time for one question before we actually start the poster session. So I was actually quite keen on you know, when you talked about scalability, but also the data reduction by orders of magnitude. So you mentioned that to run an experiment using HPC is about 100K a week. So I was wondering if you have already translated the savings that you are currently foreseeing and seeing already with some of the first results into financial savings. Yeah. And in addition to that, also the time to actually get a specific result, because I guess that these HPC simulations are also very, very heavy, and they take quite some time to actually produce results. So, you know, this two dimensions, so the cost part and also the time saving.
Yeah. So what we did, for example, one of our scientists, Tobias Dornheim, is an expert in density functional theory, and that's one of those simulations that usually runs on huge supercomputers. And he has been developing an AI-based model exactly of these kind of capabilities for mainly a huge parameter set that can be covered by these experiments. So this basically covers all the parameter ranges we will need in the future for experiments. And this was a huge task on supercomputers that took months of actually collecting that data. But in the end, this model now includes all the relevant information, and it can be easily used by scientists. It can be downloaded. It's open source. It's well documented. The data sets that led to this are even accessible. So what you can really do now is look at this model, take this model, and it's currently being implemented in a lot of other simulations that would usually not have access to this, and can be freely used by all the scientists in the world. And there are thousands of scientists that need this kind of information and can now run this on their laptops. And I think this by itself is a huge saving. Though we put a lot of HPC power in that, finally we can now deliver this to thousands of scientists and for all eternal future, basically, to be used. And this is the power of making your models open and sharing that information with others.
This is actually very, very remarkable. So I also have another question that I will release. So do you, we are supposed to start the poster session in 2 minutes, but maybe you can still take this one. So the question is from David. Do you use any intermediate reduced order model along with a neural net in physics-informed neural nets? Or is the DFT or TST simulation directly connected to neural nets? So I see you're having issues with the connection. So I don't know if you heard me. Okay, maybe not. So I think we can conclude. Let me pause.